covers the first part of section 3.8, proof by contradiction. Proof by contradiction is a method of indirect proof based upon the fact that a statement P must be either true or false, but cannot be both. If we can show that assuming the statement P is false leads to a logical contradiction, a statement known to be false, then P must in fact be true. The logical basis for a proof by contradiction is the implication not P implies R and not R implies P, contained in Theorem 1.3.1 Part H. Since this is an implication, it's a tautology, which means that it is always true. So this means that if we can show that the hypothesis not P implies R and not R is true, then the conclusion P of the implication must be true. In order to show that the hypothesis is true, we suppose not P is true, or equivalently the statement P is false. We then show that this leads to a contradiction, a statement of the form R and not R for some statement R. We can then conclude that the statement P is true. This method of proof is also known by the Latin phrases reductio ad absurdum, reduction to an absurdity, or reductio ad impossibile, reduction to an impossibility. The point being that our assumption that the original statement is false leads us to deduce an absurdity or impossibility. The exact form of a proof by contradiction will depend upon the specific form of the statement to be proved, but all such proofs follow the following basic outline. Step 1, we're going to suppose that the statement P that we're trying to prove is false, or equivalently, the negation not P is true. Now, the statement P will typically involve quantifiers and logical connectives, so we usually determine the negation not P and then suppose the negation is true. Step 2, we show that this assumption leads to a contradiction. So we need to deduce a contradiction, R and not R, from the supposition that P is false. Note that the statement R is not specified at the beginning of the proof, but is usually determined from the supposition. Either R or not R may in fact be part of the supposition. Finally, step 3, we conclude that the statement P is true. A contradiction arising out of our supposition that P is false enables us to conclude that P must be true. The proof is then complete once we obtain the contradiction. With any proof, it's important to keep the reader informed about the procedure being used. It's particularly important with a proof by contradiction since you are starting by assuming that the statement to be proved is false. One of the classic proofs by contradiction, dating all the way back to the 4th century BC, is the proof that square root of 2 is irrational. The version of the proof in the following example is similar to that in the 10th book of Euclid's Elements of Geometry. Euclid's proof uses the fact that any fraction a over b of two integers can be written in lowest terms, that is, in such a way that the integers a and b have no common divisors. The reason this is true is that if the numerator a and the denominator b have a common divisor, then they must have a greatest common divisor d. This follows since the set of all common divisors will be finite. We may then cancel the greatest common divisor d from both the numerator and denominator to obtain a new fraction a prime divided by b prime of two integers a prime and b prime with no common divisors, which is equal to the original fraction. For instance, the numerator and the denominator in the fraction 84 over 70 have a common divisor of 14, so we can reduce the fraction as shown. We have 84 is 14 times 6, 70 is 14 times 5, so canceling the 14, we obtain 84 over 70 is equal to 6/5. And now 6/5 has no common divisor in the numerator and denominator. The proof that square root of 2 is irrational also relies upon one other result. In section 3.2, we proved the result for all integers n, if n is odd, then n squared is odd. This is equivalent to its contrapositive, for all integers n, if n squared is even, then n is even. With these preliminary assumptions out of the way, we're now ready to start the proof. So for the example, we want to prove that square root of 2 is irrational. Now the statement we're trying to prove is just a simple statement. It has no variables, no quantifiers. So if we were to write it in symbolic form, we would just represent it by a letter p. So we need to prove the statement P, where P represents square root of 2 is irrational. So to start the proof, we're going to use a proof by contradiction. So our first step is to suppose the statement P that we're trying to prove is false, or equivalently, suppose not P, which says square root of 2 is rational, is true. We then need to derive a contradiction. Since square root of 2 is rational, then there exist integers a and b such that square root of 2 is equal to a over b. As discussed above, we can assume that a and b have no common divisors. Squaring both sides of this equation, we then obtain 2 is equal to a squared over b squared. Clearing the denominator, this implies a squared is equal to 2b squared. From this equation, we see that we have a squared is 2 times an integer, namely b squared, so that tells us that a squared must be even. From the results cited above, for all integers n, if n squared is even, then n is even. Since a squared is even, then we can conclude that a is even. Since a is even, then there exists an integer k such that a is equal to 2k. Substituting this into the equation a squared equal 2b squared, we obtain 2k quantity squared is equal to 2b squared, and that gives us 4k squared is 2b squared. And now canceling 2 from both sides, we obtain 2k squared is equal to b squared. This last equation implies that b squared must be even, which then implies that b is even. And this means that there exists an integer L such that b is equal to 2L. We've now shown that a is equal to 2k for some integer k, and b is equal to 2L for some integer L. It then follows that a and b have a common divisor of 2. This gives us a contradiction. So our contradiction has the form R and not R, where R is the statement a and b have a common divisor, and not R will be the statement a and b have no common divisors. So we assumed not R at the beginning of the proof. We assume that a and b have no common divisors, and we've now shown that R must be true, namely that a and b have a common divisor. So we now have R and not R, and it then follows from the implication, not P implies R and not R implies P, that P must be true. So we've shown that the hypothesis in this implication is true. We started by supposing the hypothesis, not P, and we've shown that that leads to a contradiction, R and not R. So since this is an implication, we are able to conclude that P must be true. And thus our result, P, square root of 2 is irrational, must be true. Now, one of the major differences between the method of proof by contradiction and other methods of proof is that in a proof by contradiction, in general, we do not specifically know what we need to show. In other methods of proof, we do generally know what we need to show. For instance, in a direct proof of a conditional statement P implies Q, we suppose the hypothesis P is true. We then need to show the conclusion Q is true. In a proof by contrapositive of P implies Q, we suppose the negation of the conclusion, not Q. We then need to show the negation of the hypothesis, not P. In a proof by contradiction, however, we only know that we need to derive a contradiction. That is, a statement of the general form R and not R. The statement R may be one of the assumptions or suppositions at the beginning of the proof, or may be a statement which we know to be true from a previously proved result or from our general mathematical knowledge, and very often the statement R falls into one of these categories. But in general, we do not know what the statement R is until we actually derive a contradiction. For this reason, we need to focus on our assumptions in a proof by contradiction rather than on what we need to show. For instance, in the preceding example, we obtained the contradiction R and not R, where R is A and B have a common divisor, and not R is A and B have no common divisors. We assumed at the outset of the proof, with justification, that not R is true. We then showed in the course of the proof that R must also be true. A proof by contradiction can be applied in theory to any form of statement. For instance, suppose we want to prove a theorem with the general form for all x, p of x implies q of x, using a proof by contradiction. We start by supposing this statement is false. This is equivalent to supposing the negation, there exists an x such that p of x and not q of x is true. That is, we suppose there exists an element x in the domain such that p of x is true, but q of x is false. We then need to show that this supposition leads to a contradiction. This is illustrated in the next example, where we prove the result used in the proof that square root of 2 is irrational. So for this example, we want to prove for all integers n, if n squared is odd, then n is odd. This has symbolic form for all n and z, n squared is odd implies n is odd. So using a proof by contradiction, we start by supposing the statement is false, or equivalently, the negation is true. So we suppose the negation, and the negation is there exists an n such that n squared is odd and n is not odd, or n is even. That is, suppose there exists an integer n such that n squared is odd, but n is even. We then need to derive a contradiction. Since n is even, then there exists an integer k such that n is equal to 2k. Squaring this equation, we obtain n squared is equal to 2k quantity squared, which is 4k squared. This implies n squared is equal to 2 times 2k squared. And since k is an integer, then 2k squared is an integer. So we now have n squared is 2 times 2k squared, where 2k squared is an integer. So n squared is 2 times an integer. It then follows that n squared is even. But we assumed at the beginning of the proof that n squared is odd. So this yields the contradiction, r and not r, where r is n squared is odd, and not r is that n squared is even. Since we've now derived a contradiction, we can conclude that the original statement must be true. And this completes the proof.